today we actually got a couple requests of questions to answer, but they both are revolving around the same question, and this is the idea of axial versus equatorial for cyclohexane. So let me go ahead and kind of answer that question first, because I'm seeing the same common confusion, and well, first I need to build my model. But the idea of if something is axial versus equatorial, it's based on the 2D drawing. So let me build up my molecule. So one of the common misconceptions I see about axial and equatorial is that cis-trans, those wedge bond drawings here, are going to really tell you if something is axial or equatorial, and that's not true. And the reason it's not true is because axial and equatorial positions flip quite regularly, actually. So, I promise you, I'm almost done building the model. Oh. I'm trying to find colors that make it really easy to see what I'm doing, and apparently I don't have that many of certain colors that I really want. Almost done building the model, I promise. I promise you, for all the time I'm taking like building this model, there's actually a good reason for it. Get a quick question in the chat. Quick question for Orgo 2. I'd like to revisit the discussion board and ask for the complete mechanism for number 2 and number 3. Wrong course. So to build the models, the program I'm using is ACD ChemDraw. It's a freeware version. It works well for Macintosh, or works well for PC. If you're working with a Mac, I'd recommend ChemDraw. There's a freeware version of it, and there's also, I think, Melvin Sketch. But if you just Google organic chemistry drawing software Mac, the first 3 are actually pretty good compounds, or pretty good programs. But ACD ChemDraw, I particularly like them. They're good about not spamming your inbox. And it's it's akin to the program called ChemDraw, which is what I used to use a lot. All right. So for the Orgo 2, and then I'll get back to the Orgo 1 on the axial equatorial, because it's going to require a little bit more explanation. So the first thing you make is the isopropoxide. And got asked about the big base, that they were bad leaving groups. It is a bad leaving group. What you're going to get more is a mixture of, there are going to be some hydrogen exchange, but the big thing here is that your tert butoxide is going to grab a hydrogen, and, oops, sorry. Excuse me. And when it grabs the hydrogen, this bond is going to come down. We're going to displace the OH group, and we're going to end up getting the hydroxide and the tert butanol. So it's kind of a matter of reducing who's a good base. So even if you get rid of the hydrogen off of the isopropoxide is also a big bulky base. It's going to be very good at doing elimination. So between your tert butoxide and your isopropoxides, eventually you're going to get an attack of this hydrogen that's on the secondary carbon or tertiary carbon of the isopropoxide. And you remove the hydrogen, form alone unpaired electrons, these are going to come down, form a double bond with this carbon, and displace the OH. The OH here is actually the weakest base, which is why it's the one left standing. Now for number 3, okay, I'm assuming you mean the mechanism to make 3 from 2 and the mechanism to make 2 from 3, or 1 from 2, or 2 from 1. So in terms of how we make this compound, it's a little hand wavy, but what we end up doing is we have a lone pair attack of the ether onto the water. And this is going to temporarily give us a hydronium-like ion. And honestly, we can do this with H3O+. This is why it's an acid catalyzed reaction. So we end up generating this hydronium-like ion, and then we get OH- attack from the water. Because we are in water, and water auto-dissociates to give us this OH-. So the OH- going to attack the carbon, break the bond, and we'll end up getting 2 of these molecules. So this is the mechanism for making number 2 from number 1, and the mechanism I had up here was the mechanism for making number 3 from number 2. Now, what I've got written on the discussion board, not a practical way to do it because the water would immediately react with the tertiary oxide, so you have to do a purification. Wouldn't be worth it, but this is just a hypothetical scenario. All right, back to axial versus equatorial. So when we look at a 2D drawing of cyclohexane, and we see the wedges and we see the dashes, the thing is that this isn't real. And the reason it's not real, you're welcome. The reason this isn't real is that cyclohexane does not exist as a flat 6-membered ring. So as drawn, take off all my groups first. I don't really have that structure. So the way that's drawn, this is how you would actually build the molecule. Is you would take your 6-membered ring and you'd crush it down into the planar. Modeling kits get kind of flexible. You're going to crush it down into a plane. So this is literally what's drawn up on this board. We have a flat ring, and we have 2 methyl groups popping out. But neither of these are axial or equatorial because we only get the axial equatorial when we're in the boat conformation. So for the boat conformation, I take my ring, and I'm going to take one, I'm going to pop it up, I'm going to take the one opposite and pop it down. And now I have this boat, I have this chair conformation. So I've got the feet, a little bit clearer here. I got the arms, I got the head, and I got the feet. So when I did this, one ended up being axial and the other ended up being equatorial. And I can flip them. So because cyclohexane is flexible, now I can take one of my axial groups and make it equatorial. So to make this a little bit easier to see, my axial groups are the ones that, if I were to sit the boat conformation flat on a table, they're the ones that stick up and down. Like this. My equatorial are the ones that pop off away from the ring. And they kind of go up and down. They're not perfectly equatorial, but more or less they have a lot more space. So this is really what the molecule looks like. I've got 3 axials that are up, 3 axials that are down, and 6 equatorials. But again, I can flip this ring. And if I flip this ring, what you'll see is now all those atoms that were axial or were all equatorial, now they're up axial, down axial, and all the ones that were axial equatorial now, axial up and down, are now equatorial. So this is not the reality. The reality is that part of it goes up, which would make the methyl group pop up, the feet go down, And when I do this, this methyl group ends up hanging off on the equatorial position. So when we talk about axial equatorial when it comes to cis-trans, what we're really saying is, are they both axial and both equatorial, or is one axial and one equatorial? But we're not going to specify if they're actually axial or they're actually equatorial, because they can interconvert between the two. The question is not whether or not they're the same. So what I can do to figure this out is I'm going to take a red group and a blue group, and I'm going to make them the only two on the ring. And I'm going to make them cis. So to make them cis, I crash my ring out until it's flat. So like that. And then I'm going to take one of them and I'm going to pop it up and pop the other one down. And now I can see that one is axial, one is equatorial. So the question is, how many atoms apart are they? So this is 1, 2, 3, and if I go by symmetry, it ends up being the reverse. So where's the second? Well, if it's 1 away, we'll talk about it, it's 2 away. If they're cis, then they're opposite. So this is axial equatorial. And they end up being opposite because in order to pop this one out, this one, it bends the second position, the top position, into the equatorial position. Now let's say if I start with them both trans, it's kind of hard to build, particularly with this molecule getting so old. So I build them trans. Now if I pop one up and make it axial, now they're both axial. And if they're just 1 unit away, they end up being opposite axials. Now, let's say I go to the second position. So let's say I go, I'm missing my pens. Oh, wait, got another one. Here we go. Got green. So let's say I put one on the green position. So now it's 2 atoms away, 2 carbons away from the group I'm looking at. So now if I make them both cis and I pop one up into the boat conformation, they end up both being, come on, up. They end up both being axial. So in this case, if they're cis, they're both axial or equatorial. And if it's trans, it's the opposite. One's axial, equatorial. Now if I go to the third position, it's actually going to be the same as the first position. So if I do +1 or +3. So if I put them 3 carbons apart, so I got my Planar 3 apart, I pop one up and pop the other one down. One's axial, one's equatorial if they started out cis, and they'll actually be on opposite sides. Or I'm sorry. If it's trans, so if I go back to building it, so if I end up building the plane and then I end up making them trans, I get that one is they're both axial or they're both, come on, you can do it. They're both axial or they're both equatorial, and if they're both axial, they're on opposite sides. So off the bat, how do you figure out if they're axial or equatorial? Well, you can just use this flow diagram or you can build the model. But the thing is to keep in mind, this is not the both conformation. This is the planar conformation. It's the high energy conformation that it doesn't exist in. But it makes it easy for identifying cis-trans. Now, this is going to pop into the boat conformation when it gets done. So when it pops in the boat conformation, are they both going to be axial or equatorial, or is one going to be axial and one going to be equatorial? And we figure that out by either, again, looking at this flow diagram or just building the model. So if they're cis and they're 1 or 3 apart, they end up alternating axial equatorial. So if this one's up, this will end up being, if this one's axial, this will end up being equatorial, or if this is axial, this will end up being equatorial. If they're trans, they're the same. So if I were to draw a wedge here, I'm sorry, a dash here, if this is axial, this is axial. This is equatorial, this is also equatorial. And it just flips if they're between the two. So in terms of the discussion board, you get this question. So I'll do the first two for you. So again, the easiest thing to do is build the model. So I'm going to take my model, depending on what I did with it. There you go. And I've got my methyl group and I've got my ethyl group. And this is drawn as planar, so I'm going to build it like it's planar. So I got my planar ring. First one, my methyl group goes up. And then my ethyl group is opposite. They're trans. So that I would call this trans 1-ethyl, 2-methyl cyclohexane. Now I need to pop it into the boat conformation. It doesn't matter which one I pop up or down because all I'm looking at is the relative configurations. So if I look at it, they're both axial, which means that they're both axial, or if I flip the ring around, they're both equatorial. So for number one, I would say that the two groups are both axial and equatorial, but they're the same. So they could be axial, they could be equatorial. In this case, we prefer them both to be equatorial because bulky groups prefer the equatorial position. But that's how that would work. For two, we're going to build it again. We've got our methyl group now going down, and we've got our ethyl group going up. And we're going to start with the planar conformation. We got our methyl group going down, our ethyl group going up, and then we're going to let it go into the boat conformation. And when I do this, I have the ethyl group being axial and the methyl group being equatorial. So they are opposite in this case, and if I flip the ring, it still ends up being the same thing. The ethyl group is going to be equatorial while the methyl group is axial. So I would say that for number two, they are opposite. One is axial, one is equatorial. But because there is ring flipping, I can't say one is axial and the other is equatorial. I expect the ethyl group being larger to be in the equatorial position most of the time, but they can easily interconvert. Now, also got a question I've asked about with these rings concerning Rns configuration. For these, that's where the cis-trans comes from. So if we just have two groups on the ring, we don't need the Rs because the cis-trans here is going to specify the geometry for us. So let's say we go with example 1. You could try to specify the Rs, and it can be done. These are chiral centers. But here's the thing, that's a lot of work. What's easier to do is just use the cis-trans. So here the cis-trans refers to the hydrogen. So the hydrogen in this case are on opposite sides. So this ends up being E 1-ethyl 2-methyl cyclohexane. Or we can do cis-trans. So in terms of the cis-trans, this is trans, with trans referring to the hydrogens, 1-ethyl 2-methyl cyclohexane. Now, a bad habit you can get into with this is assuming that cis-trans and EZ are the same. They're not. EZ is the more general case. So you can always name something by EZ notation. You can't always name things by cis-trans notation. So let's say I had a fluorine here. So if I had fluorine, there is nothing that is cis-trans relative to each other. So for cis-trans, we have to have two groups that are the same. In the case of 4 things specified stereochemistry, so we got a methyl, a fluorine, an ethyl, and a hydrogen, now we have to use the EZ and we have to look at priority rules. So in this case, the higher priority group is down, so fluorine is 1, ethyl group is down, so that's going to end up being highest group here. And so this ends up being Z. So this is Z 1-ethyl 2-methyl cyclohexane. There are situations where there are cis and trans. Again, for hydrocarbons, the EZ cis-tran are going to agree simply because priority is set by carbon. The EZ is going to become a lot harder when you start going to alcohols and alkyl halides, and you may have two hydroxyl groups that are opposite or that are cis-trans relative to each other, but because of what's bound opposite to them, it may not necessarily correspond to the same EZ. So now I'm getting to a specific question. You can explain question 56, part 2, 4, and 6 on your live stream. So let me bring that up. By the way, those of you in Organic 1, I really hope that you caught that your exam's due Sunday. It was in the announcement. I forgot to bring it up, but it's definitely an announcement in the course calendar. Question 56. So identify the most stable 1,4-dimethyl cyclohexane with methyl substitutions at 2 and 3. Easy answer for any of these. It's giving a whole bunch. Anything that puts all the groups that aren't hydrogen equatorial, that's the lowest energy. So the answer for 1 out of 6 is the one where they're both equatorial. And it says in this case the methyl substitutions are both, well, now you have to build the molecule. So if we build our chair conformation, this is why you really need to be working with your modeling kits. So in this case, I've got my chair. I've got one equatorial, the other equatorial. When I build this back into the planar conformation, this ends up making them trans. So again, don't get into the habit of thinking that cis-trans refer to axial equatorial. Cis-trans refers to if it's in a planar conformation. Equatorial, axial refers to when it's in the boat conformation. Next question, identify the structure of 1,2-cyclohexane using position C12 where both methyl are both equatorial. Identify the structure of 1,2-dimethyl cyclohexane using position C1C2 where both methyl substituents are in equatorial positions. And I'll share the desktop with you. So in this case, they're both equatorial when they're not up and down. Now, are these groups axial or equatorial to, well, or are these cis-trans? So again, the easiest thing to do here, we've got our chair conformation built. We've got both groups being beside each other and both being equatorial. So when I take my model, they're both equatorial, they're both kind of hanging off the side. And now I'm going to crush it down until it's in the planar conformation. And now that it's planar, you can see that they're trans. So when I go back to the question, they're both trans. Identify the structure where one methyl group is axial at C2 and the other is equatorial. So we're looking for one being up and down, the other pointed out. And the trick with this one is also making sure the correct number of carbons apart. So these are both axial. This is one axial equatorial. This is one axial equatorial, and these are both equatorial. So C2, I believe the top right starts as C1. So C2 is axial. So it's going to be this one, axial, equatorial. Yep. Now, whether or not these are cis-trans relative to each other. Again, I'm going to build my chair conformation. And I've got one going down. And I've got the other sitting off axial. So if you look at that structure, this is what it looks like. I've got the one going down, the other being equatorial. Honestly, the nice thing about the symmetry with this, it doesn't matter. I mean, the program's going to penalize you for not considering what's C1. Honestly, by rotation, you can put them wherever you want, as long as they're the correct number of carbons apart, one's axial, one equatorial. But if I end up crushing it down, I see that they're both cis to one another. So in terms of what these are relative to each other, these are both cis, and that's it. So again, going backwards, my honest advice to you is take your modeling kit. You're free to use these on exam, and this is why I encourage you to buy the model kits and use them. A lot of this is your ability to do spatial reasoning, and it's not easy to do. It's taken me 3 semesters now to get to the point that I can kind of see these things in my head. But definitely the first semester I taught this, I was heavily reliant on the modeling kit. So, any other questions out there? Hopefully I answered the questions that I got sent. Orgo, packet 2, Orgo 1, page 23. All right, let me bring that up. This computer's a little slow, so give it a minute. Still loading. So page 23, you can explain the ability of the third and fourth pair. So the third pair, one axial equatorial. And then we have this one axial equatorial. So you can argue they're both kind of the same. There is no benefit to doing axial equatorial because they're both, one's axial, one equatorial. So I would definitely say they're both the same. And also in terms of just how far apart they are, that's not going to have a huge difference. But definitely for the next one down, the reason why it says, because it's meant to be one that makes you kind of think. In terms of this, the only reason why I would say that B is more stable, because they're both axial, which means that when we do the flip, they can both be equatorial, so we get the stability there. At this point, it's just pure sterics. So In the case of B, there is a stable conformation, but case of the third one, we're trading off between axial and equatorial, so there's really no benefit, and honestly, they're not that close together. But when they're on adjacent carbons, even though they can both be equatorial, they're still going to push off of each other. So B in this case ends up being more stable just because when they're both equatorial, they're both far apart. So I hope that answered your question. But with the fourth pair, they can both be equatorial, which means there's a stable conformation. So anything that gets those equatorial groups far away is going to make it more stable. For number 3, because they're alternating axial equatorial, they're never in the same plane, so there's none of the steric issues. Yeah, there's no steric issues because they're never occupying the same plane. Also, could you go over drawing cycloalkanes when you're given their 2D chair projection? Yeah, if they weren't for this one, if they were both equatorial or they were both axial, both equatorial, then you can make the case they were further away. But because they're not sitting in the same plane, they don't interact with each other. All right. Now, for the 2D projections to 3D projections, actually keep in mind with this, it does make the comment there, if your answer contains the same stereochemistry, for example, Z or cis, then your answer is probably also correct. There is interconversion between axial and equatorial. So the only restriction here is that based on the stereo drawing, do we expect them to both be axial or both equatorial, meaning that they occupy the same position, or do we expect one to be axial and equatorial? So for the first one, we have this structure. And the answer it gives is this, but we can also flip the ring, and we can get this. So both of these are correct answers. The stipulation here for the 2D projection is that they're both axial or they're both equatorial. So the easiest way to build these structures, or figure out how to do this 2D projection from the 3D projection, build your planar cyclohexane, and then just add the substituents where they belong. So I've got these groups are going to be trans to each other, 4 carbons apart. So I've got the molecule, and then you just put it into the boat conformation. And when I do the boat conformation here, you can see that they're both axial, which is what I've drawn for the 2D projection. Or if you flip it, they end up being both equatorial. But the point here is that when you draw it, both are axial or both are equatorial. If you go to the next one down, ooh, that's not a good example. Ooh, the one after it. So the second example on page 20. You build this ring, and you've got 3 groups that are cis to each other. So you got this structure. Now we just have to put it into the chair conformation. So I'm going to take one, pop it up, and take another one, pop it down. And what I see is that I have 2 that are axial and 1 that's equatorial. So one is going to be opposite the other 2, and the 2 that are next to each other, they're going to be opposites. So the way the structure is drawn in the key is like this, but we can flip the axial equatorial positions. Like we can do ring flipping. So we could get that as well. And, oops, sorry, flipped in the wrong way. But I can easily make that happen. All I gotta do is pop 1 carbon up, and now 1 group is axial and the other 2 are equatorial. So for the 2D projection, my recommendation is to build the molecule as a 2D projection. So take your cyclohexane ring, crash it down into a plane, crush it down to a plane, build your cis strands, and then take 2 carbons that are opposite from each other on the ring, pop one up, put the other one down, and now you're in the boat conformation. and look at the relative orientations. How many are axial and how many are equatorial, and what are they relative to each other? So again, for this stereo drawing, second example on page 20, one is going to be axial, the other two are going to be equatorial. The two that are adjacent to each other occupy opposite axial equatorial. One's axial, the other's equatorial. The one that's separated by a carbon, those are both going to be axial or equatorial relative to each other. Can you go over question 20 and question 32 on the Oregon 1 test 2 homework? So let me go to question 20. Well, first got to bring up the page. Just a minute. What is the hybridization of each carbon? So I'm going to tell you all about, I hate hybridization. I hate the fact we teach hybridization, and this is the inorganic chemist in me. So if there's any like tone of disdain in my voice, I'm sorry, but I'm not sorry that I've had this disdain for it. So we try to use hybridization synonymously with geometry. Not the best thing in the world, but whatever. So how do you figure out if a carbon is sp, sp2, or sp3 hybridized? Well, what we do is look at the number of atoms around it. So if it's sp hybridized, it has 2 atoms around it. If it's sp2, it's got 3, and if it's sp3, it's got 4. And these atoms are going to include hydrogen, so those hydrogens aren't shown in the line bond drawing. So if we've got A, B, C, D, E. So for A, we've got, this carbon has 1, 2, 3, 4 atoms around it. So this ends up being sp3 hybridized. For B, we've got 1, 2, 3 atoms around it, so it's sp2. For C, there's a hidden hydrogen. There's 1, 2, 3 atoms around it, so it's sp2. For this carbon, we've got 1, 2, no hydrogens, so it's sp. And for E, we've got a hydrogen hanging off the end. So this carbon has 1, 2 hydrogens near it, so it's sp hybridized. So that's the quick and dirty way to figure out what the hybridization is. And the bond angles, if it's sp hybridized, it's 180. sp2, it's 120. And then sp3, I think, is 104.9, something like that. So whatever the angle of a tetrahedral atom is. Yeah, so angle ABC is going to be 120. Angle BCD, also 120. And angle CDE is 180 degrees. Oh, mercifully, they don't make you do the tetrahedral. But that's just stuff to memorize. I don't think it shows up on the test very much at all, if at all. Question 32. It's probably going to make you do a superscript. So, tell you what, let me answer question 32 because it just loaded. And then we'll go back to how to format. So question 32. From among the 18 constitutional isomers of C8H18, write the structural formulas and give the IUPAC names for those that are named as derivatives of heptane. So heptane, hept is 7. First thing is it's saturated. So if we look at it, CnH2n plus 2, 18, so there's no rings and no double bonds. So heptane is C7. 1, 2, 3, 4, 5, 6, 7. Now there is a mirror plane in this molecule, so we're looking for ones where we would get a unique name. So it already tells you there's 3. So we can't put a methyl group here because that would give us octane. So we have to go to the first one. So this would be 1-methyl heptane. Next option, go to the second carbon. This would be 2-methyl heptane. And then go to the 3 carbon, which would give us 3-methyl. Now, if we put one here, the reason I'm drawing this line down the center, we can just rotate it around and get back to this one. So that's why you only have 3 unique positions. So, just so you can see it on your end, let me switch to the desktop. So let's go with 2-methyl heptane. One, 2, 3, 4, 5, 6, 7. It's gonna be real embarrassing if this doesn't work. Yep, and that's one on the 2-methyl heptane. Next one will be 3 with 1 there. Next will be 4 with the methyl group up. Now to go back to question 20. And I'm hoping you can see it on your end. I don't know how good the resolution is on your end or even on my end. But here's hoping. So the hybridization of A would be SP superscript 3. And if I check it, you can see it there, it'll accept it. So I think if you type SP3, it won't do anything for you. You've got to select this superscript. And SP. I'm curious. SP. Right. And then the bond angles. 20, 120, 180. Yeah, so it's just a matter of using the superscript key. But if you just type SP3 or SP2, it's just going to reject it. Sometimes I think students are freaked out when I show them how to do the homework and do the homework in front of them. The point of the homework is not to penalize you. That's what the exam's for. So yeah, I have no problems answering the homework questions in front of you. But sometimes it's also good just to diagnose what goes on. Yeah, you're welcome. It's one thing when you're getting it wrong because you're actually wrong. It's another thing when you're getting it wrong just because it's stupid formatting issues. Yeah, particularly at the beginning of the semester when I do WebAssign, a lot of the issues are more just formatting issues in WebAssign. So I tell students, just let me know what you're doing. Or at least with WebAssign, I can see what you're doing. Just let me know if you're struggling because, again, sometimes it is just legitimate formatting issues. You have the right answer, it's just not entered correctly. All right, so going over the second one here, going back to the drawing. So so I got a question about converting this one. Back to a stereo drawing. So easiest thing again, build your conformation. And what I'm going to do, I've got 4 groups. 1, 2, 3, 4. I'm going to alternate red, black just to make them a little bit easier to see. So my 2 axials, they're on opposite sides of the ring. One points up, one points down. And then my 2 equatorials are also on opposite sides, but adjacent to the 2 axials. So this is the 2D projection of that structure. In order to get it to a stereo drawing, I'm just going to press it down until I recover a flat cyclohexane ring. Can you do it for me? So when I crush it down, it's not going to behave well for me. What I see is I have 2 groups that are up and 2 groups that are down. So if I just build that chair conformation and then add the axial and equatorial groups manually, and then crush that chair conformation down to a boat conformation, this is what I end up getting. So if I just draw that projection, or draw that structure, I have 2 that are cis, and opposite of them are 2 groups that are trans. So yeah, that's how I would recommend doing it. And you're free to use your modeling kits on your tests. Like, that's why you buy them. Other questions? Test 2 should just be 20 questions. Let me open it up on my end. Yep, 20 questions, 100 points total. 75 minutes to take the exam unless you have extra time for DSS. Nothing too out of left field with this test. You're welcome. Start whittling down my inbox while I'm at it. All right, so that's it for questions. Again, Orgo 1, wish I had reminded you earlier this week, but it's on the calendar and syllabus and the announcement and the grade book. You do have an exam due Sunday at midnight. It's going to lock you out if you have less than 75 minutes to take the exam. So make sure you take it with plenty of time. Open notes, open resources, just again, only stuff that you have in class, no one helping you out, no going on to Reddit to post questions because I do fish Reddit. And next week, Orgo 2, you guys start your exams on Monday. So I'm expecting a lot more Orgo 2 questions next week. But as with any live stream, again, feel free to submit questions in advance. Feel free to post about them in the chat. I've got Teams open, so if you got questions, you can post them there. And I will see you all Monday.